Welcome back, everybody, to INE CCIE Data Center Nexus switching class. In this section, we're going to be continuing our discussion of Fabricpath. We're going to take a look at some examples of the Nexus 5000, talking to the 7K with Fabricpath, then get into some more of the details of what's going on behind the scenes with IS to IS. How do we exchange the switch IDs for solving the shortest path tree? How do we actually learn the MAC addresses and then ultimately forward the traffic over the layer 2 network? So let's take a look back at our diagram that we're using here. Right now, the way that I had the previous example set up is that we have the 4 different end devices that we're using for testing, the 2 servers and the 2 routers. And the 5Ks were directly connected over this E1/1 link that I had configured Fabricpath on. Now, the main idea behind this is that we're not going to be running spanning tree over that link. We're also changing the MAC address learning behavior. We're changing from the traditional MAC learning to the conversational learning, which means that we can cut down on some of the control plane information, or essentially just the amount of MAC addresses that we have in the layer 2 CAM table. So what we're going to do now is to start to expand the Fabricpath domain upstream, and I'm going to be doing this just in a point-to-point manner so that we do not have additional redundant links, so we can see exactly how traffic is going to forward. Once we get done with that, we'll start to add some of these additional interconnections and then see what the result is going to be from layer 2 forwarding. Now, as we saw in the 5Ks, the configuration of this feature is very, very simple. Again, there are literally 4 commands that we need to do. We go to global config and say install feature set Fabricpath. We say then feature set Fabricpath. That is turning the feature on. Okay, I need to do this on all of these devices. So feature set Fabricpath. In the case of the VDCs, these 4 7Ks are all part of the same chassis. So I only need to install the feature set in the default VDC. Then it's going to be available for usage by all of the user VDCs. If we also look at the show run VDC on the default VDC, we'll see a command here that says to allow the feature set Fabricpath. So I do need to make sure that this is listed under the individual VDC numbers. It will be by default, but if for some reason we went in there and said no allow feature set Fabricpath, it means that those particular virtual device contexts would not be able to run the feature. So simply based on the fact that I was able to issue the feature set Fabricpath on all of them and it did not give me an error message, I know that the default VDC is set up in such a way that it's going to allow the feature. So next I need to know what are the VLAN numbers that I'm actually trying to send over the Fabricpath domain. So again, I go under the VLAN mode, in this case VLAN 10, and we say the mode is Fabricpath. So this is going to be on everyone, both on the leaf switches and on the spine switches. So VLAN 10, the mode is Fabricpath. VLAN 10, mode Fabricpath. Because everyone needs to agree what VLANs are going to be changing their MAC address for MAC address learning, so from traditional, I should say, to conversational, and which VLANs are we going to be forming the adjacencies over for IS to IS. So the mode then is Fabricpath. Next, we need to go to our layer 2 interconnect. So starting on the 5Ks, we're going to say here that this is on interface E1 8 to 9. Interface E1 8 to 9. The switch port mode will be Fabricpath and no shutdown. On the 7K, likewise, these are going to be interfaces E2 3 to 4 and E2 7. Switch port mode Fabricpath and no shutdown. On 7K 1-3, interfaces E2 23, E2 17 to 18. Switch port mode Fabricpath and no shut. On 7K 1-4, this is interface E2 31 and E2 25 to 26. Switch port mode Fabricpath, no shutdown. Then on 7K 1-2, I have interfaces E2 15 and E2 11 to 12. Now notice again that these are all F1 ports. So the M1 modules do not support this feature. switch port mode Fabricpath, no shutdown, and then on 5K2. So interface E1 8 to 9, switch port mode Fabricpath, and no shutdown. This technically would be my full final functional config. This is the only thing that I need to do. Let's actually look at the forwarding now. So let's go, before we verify anything in the control plane, let's go to the servers here. And I want to generate some traffic to see, can I actually get the traffic to forward over Fabricpath. So if we look at their link properties, these should all be in VLAN 10. So this here is server 3. Its address is 10.00.30. Then I have server 1 here. Server 1 is 10.00.10, so they're in the same subnet. Now, someone had a question on the break. Is there a special teaming mechanism for Fabricpath? As of yet, no. So down to the end servers, you're going to be running your normal, just layer 2 classical Ethernet. Again, the reason why is that Fabricpath is not Ethernet. Fabricpath is its own layer 2 protocol. Even though it's using MAC addresses, which are really the switch IDs, it's a completely separate protocol. It has a different ether type for the data center Ethernet and is not supported over normal, regular layer 2 Ethernet links. Okay, the next thing I'm going to do here is to generate some traffic between the servers. So I'm going to send TCP packets. This is going to go, we'll say that this device is, let's see, is this server 1 or 2? This is server 1 here, will be the server. So server 1 is listening for TCP traffic. And server 3, let's generate the traffic. So TCP, want to make sure I have a large window size. I'll say also my maximum segment size is large, let's say 9,000 bytes or so. Then the server is 10.00.10. Now, since this is only one individual flow, we can see we're only getting the bandwidth of one physical link. So let me stop this. Let's change this to the units in gigabits per second so it's a little bit easier to read. And I'm going to send multiple flows. Let's say we send 8 flows. And then I believe on the server, I need to start and stop the process again. So basically, every time you run this, you have to start and stop it again. So I now have 8 flows, and let's see, what is the aggregate of the bandwidth? The aggregate is starting to crawl up. Okay, so there it's about 2 gigs. So it should be about line rate that we're getting now. So now let's take a look at how is the traffic actually forwarded. If we go back to our topology, the traffic is coming in from server 3, so this is the TCP traffic generator. It's going to 5K2. We have 2 links on our uplinks, E18 and E19. So let's go to 5K2. Let's look at show interfaces E1 8 to 9. And I want to know, let's also set these both to load interval counter number 2 is 30 seconds. So we don't have to wait 5 minutes to see how much traffic is being sent. So show interfaces E1 8 to 9, and I want to know what is the output rate. So the output rate between them is actually equal. So we have 1 gig on the first link, we have almost 1 gig on the second link. This again is because we're now using IS to IS's shortest path tree in order to route the traffic. This is not an ether channel load balancing mechanism. It's basically layer 2 routing. So what we need to know is, how did Nexus 2K2, or 5K2 in this case, how did it know that that destination switch was actually located out both of those ports individually. So let's look at from the switch that it is actually attached to. If we look at the show MAC address table dynamic for VLAN 10, this address here, the DAFA, this is the end host. That was the TCP server that we're sending the traffic to. So now let's start to go up into the core and look at what do the other switches in the middle know about this server. So this server's MAC address, again, ends in DAFA. That's what we're looking for. So let's go up to 7K1-1, and we will show MAC address table dynamic VLAN 10. DAFA, we have this MAC address listed in here. But notice what is the destination. The destination is not a connected physical port. Instead, what this actually is the Fabricpath switch identifier. So this number here, this is automatically generated once we start the Fabricpath process. And again, this would typically be why you would want to change the Fabricpath switch identifier manually. So from a verification and a troubleshooting point of view, it's going to make it a little bit easier for us to figure out which switches is it actually telling us that these devices are located on. So that's the next step I'm going to do here before going further with the verification, is to change the switch IDs. So let's go to global configuration on 5K1, and we're going to say that the Fabricpath switch ID is 51. This is for 5K1. So continuing on to 5K2, let's say that the Fabricpath switch identifier is 52. On 7K1, I'll say that the Fabricpath switch ID is 71. And so on and so forth. Again, just to make sure that our verification is a little bit cleaner. Fabricpath switch ID 72. Fabricpath switch ID 73. And Fabricpath switch ID is 74. Now, to make sure that this is actually going to apply, I'm not 100% sure if this is an event-driven process, but in any case, we can force it to apply by saying clear Fabricpath ISIS adjacencies. That's going to reset our layer 2 ISIS process. And let's turn monitoring on to the console, or to the VTY terminal monitor. So I'm going to say this on all of the switches. This is going to restart the Fabricpath process. This would be the same as clearing our layer 3 routing adjacencies, like clear IP OSPF process. Clear Fabricpath ISIS adjacency. So we can see some of the log messages being generated here, that there's point-to-point level 1 adjacencies that are going down. Eventually we should see that these come up. It says on multi-topology 0, this is the default topology for Fabricpath, where the idea behind this is that you theoretically could create multiple trees in Fabricpath. You have different shortest path trees. Then you could map individual VLANs onto separate multiple topology trees. I don't believe that's actually available in most of the versions yet, though. So that's a pretty new feature that's coming out with Fabricpath. So now let's look back at 7K1 and look at the same verification we did before, which is the show MAC address table dynamic for VLAN 10. Now we don't know any of the VLANs or any of the MAC addresses yet, so let's go back to the end servers and we're going to need to refresh some of this information. So on our server, I need to stop and start the process again. This was because when I cleared the layer 2 adjacency, it disconnected the TCP session, and then the traffic generator stopped sending. So we can see we do have reachability again. Bandwidth utilization is starting to climb there. We have about 0.87 gigs. So we're going through TCP slow start. Now we have about line rate. Because as we know with TCP, it starts with small exchange, listens for the acknowledgments. As the acknowledgments start to come back in, we start to increase our window size, and eventually we can theoretically eat up all the bandwidth with just the TCP protocol, which is what we're doing here, is just generating line rate traffic essentially. So now let's look at the show MAC address table dynamic. We see DAFA. Again, that's server 1. That's the listener. And then this is server 2, this is the sender. What is the key point to note here is that server 1, it says, is located on switch ID 51, which is Nexus 5K1. Then the other server, server 3, is located on switch ID 52. So essentially, this is how we are doing our layer 2 MAC routing with IS-to-IS. So IS-IS is used to exchange the switch IDs. We build the shortest path tree based on the switch IDs. Then in the actual Fabricpath data plane, what's happening here is that when the packet is coming in, it's coming in from the classical Ethernet network. So this down here, this is classical Ethernet. It comes into the Fabricpath edge router, or what we call the leaf router, leaf switch. The leaf switch is taking that TCP traffic, and we're encapsulating it. Of course, it has a regular Ethernet header. It has an IP header. It has an Ethernet header. Then we're putting the Fabricpath header on it. Now, what the Fabricpath header is saying is that the source of the traffic is in 5K2. The destination of the traffic is in 5K1. Because we already know, based on the flooding of MAC addresses, where the destinations are located. We also know, based on the IS-IS layer 2 routing exchange, who are the different nodes in the shortest path tree, so who are these switch IDs. We know the shortest path to them, and then we can encode this in the data plane. So again, essentially we're doing a Fabricpath over Ethernet tunnel, or the other way around. It's actually an Ethernet over Fabricpath tunnel that's going through the core of Fabricpath. So we will see in the middle of the network, these devices do need to know the MAC addresses about the end hosts, but since we are running that conversational learning, they are only going to know the MAC addresses that are actively forwarding the traffic. So if we look at this output basically anywhere in the topology, let's look at it on all of the switches, and then we're going to compare it. Different switches will have different copies of the CAM table. In normal layer 2 Ethernet switching, that is not the case. Essentially, all switches would have the same copy of the CAM table because we're learning based on flooding. When we flood everywhere. As long as we're talking about the same VLAN, which is VLAN 10 in this case, the VLAN 10 CAM table should be synchronized on all layer 2 switches. Now here we see the first 5K has 3 MAC addresses. We go from 5K1 to 7K1. This is our entrance from the classical Ethernet to the Fabricpath domain. We get to the Fabricpath spine switch. We have 3 MAC addresses, which are router 3, the 2 end servers, but we don't see router 2 in here. We're going through the core. We go from 1 to 3, from 3 to 4, from 4 down to 2. So all of these are learning router 3's MAC addresses in the servers, but we're not learning router 2's MAC address. Okay, notice 5K2 is learning router 2's MAC address, but it's not learning router 3's because there's not yet any unidirectional or bidirectional, I should say, communication between those end hosts. So if we were to go to router 2 and do a ping that goes over to router 3, we should see that now the devices will learn that MAC address. And essentially, this CAM table becomes the layer 2 routing table. So in the core of Fabricpath, this is one of the spine switches. It says to get to the MAC address of router 2, we need to go to switch ID 52. To get to the MAC address of router 3, we need to go to the switch ID of 51. We can then see the details of what's actually going on behind the control plane if we look at the show Fabricpath, and you'll see that there's not too many verifications we can go through here, but the control plane is going to be based on IS-to-IS. So we could say show Fabricpath IS-IS adjacency. This shows the connected neighbors that we are forming the adjacency with. If we show Fabricpath IS-IS database, this is going to show us in the overall shortest path tree who are all the switches that are making up the network. So in this case, there are 6 switches. Now, there is a feature that's enabled here under IS-IS for Fabricpath, and it's actually the same as that would run under your normal IS-IS process. But if we were to say Fabricpath domain default, this is what gets us under the IS-IS routing protocol config for Fabricpath. So there are some options that you could change here. So we could do authentication, which is going to be like our normal MD5 IS-IS authentication, but in this case, the control plane is for Fabricpath. We could change the link state packet advertisement information, like how often do we generate LSPs, what is going to be the maximum age that a link state packet can be in the database. We could change what are the timers going to be, like how often does the SPF calculation run. This would be for very, very large topologies. If we needed to do some optimization on ISIS in the background, you could actually change those. Okay, what I want to show here is if we were to say, let's also look at another one first here before I make any changes, which is show Fabricpath ISIS trees. This does show us inside the topology what are the particular switches and what links are they located out. So we can see, for example, and let's look back at our topology diagram here. Let's look at this verification from, we're looking at it on 7K1-3, I believe. Yes. Okay, and it has two adjacencies with switch 4, 7K1-4. This is via E1 or E218, which is this link here. And we see that there are other ones reachable out. Actually, let's look at the show Fabricpath ISIS adjacency. So we do have two adjacencies here. Let's now look at, let's go back under the routing config, which is the Fabricpath topology default. No, Fabricpath domain default. And I want to say no hostname dynamic. Then let's look at the show ISIS database, show Fabricpath ISIS database. Normally, ISIS runs this command automatically, hostname dynamic. The same is going to be true for your regular IPv4 or IPv6 ISIS routing. What this does normally under layer 3 ISIS routing is take your network entity title addresses, so basically your ISO NSAP format, and then convert that to the host name, because the host name is advertised as one of the TLV attributes in ISIS. Here with Fabricpath, what it's doing is hiding basically what are the outer destination addresses that are used for the actual switching of the data plane. So if we look at the output here of this, the show Fabricpath ISIS database, these essentially MAC addresses are corresponding to the individual switches that are in the topology. And these are the numbers then that would be used as part of the control plane advertisement to figure out who are the switches in the topology, what are the links that they are interconnected by, and then how do we solve the shortest path tree. So what's the resulting routing? Okay, but to simplify this, I'm going to turn this back on because otherwise we would have to constantly correlate what are the MAC addresses between the devices. So hostname dynamic, show Fabricpath ISIS adjacency, and show Fabricpath ISIS database. This tells us what are those particular devices. Okay, if we were to also look at the database detail, this shows us the actual routing. Now, I'm not going to go through all the details of decoding this because this goes into the link state behavior of ISIS and how shortest path first works with the candidate database and the shortest path tree. We basically run a mathematical search behind the scenes that figures out who are my connected neighbors, who are their connected neighbors, who are their connected neighbors, and so on and so forth. We do the recursion through the tree, we figure out what are the cost values, and then ultimately we can solve the shortest path tree by doing the mathematical search. But essentially this is what the detailed database would show you. And you could work this backwards based on looking at what are the individual switches advertising their link states. So this is the actual LSP, the link state update, or the LSP, link state packet. Okay, this is the equivalent of the link state advertising, the LSA and OSPF. So essentially what this is saying is that there is a switch, N7K1-4, who has adjacencies twice with 7K1-3 and once with 7K1-2. The ISIS metric for each of these links is 40, which means that when we actually go to route the traffic at layer 2, we now have equal cost multipath. Now we can go ahead and change these metric values, and there's minor fields that you can change that are related to ISDIS, but in 99% of the applications you don't even need to do this. And this is why Fabricpath is such a nice implementation, that you simply turn the feature set on globally, you change the mode of the VLANs to run as Fabricpath, then specify the Fabricpath core ports with your switch port mode Fabricpath, and that's pretty much all that you need to do. Now, another kind of best practice would be anytime you're running a control plane protocol, you would also want to add security to it. So whether we're talking about OTV, or talking about HSRP, VRRP, Fabricpath, you normally would want to do authentication on all of those control plane protocols, and they pretty much all support it. Where in this case, our control plane for Fabricpath is ISIS, so we would want to create a keychain, specify what the password is, then authenticate the adjacencies for Fabricpath ISIS, just to make sure that there's no misconfigurations in the network. Or if someone misconfigures a link as Fabricpath, that it's not going to change our forwarding because we wouldn't automatically establish the adjacency with them. So really, there's only a few verifications that you would need to do here. I just want to know, did I establish my adjacencies? Which again is going to be the show Fabricpath ISIS adjacency. And then what is the actual routing table, which is going to be the MAC address table. Show MAC address table dynamic VLAN 10. We could also say show Fabricpath route. This is going to show what are the different possible ways that you can reach the individual switches. So the key differentiation here, or one of the key differentiations, with the ISIS control plane of Fabricpath versus the ISIS control plane with OTV, is that OTV is used to advertise the actual end host MAC addresses. With Fabricpath, it is not. Fabricpath is used just to advertise the switch IDs in the shortest path tree. So this is basically minimizing the control plane information that ISIS needs to know. It just needs to know who are all the switches, what are their interconnections, that's the graph of the tree. Then ultimately, once I solve the shortest path tree, what is the metric to reach them? We can see here that the metric is equal between them. So as long as I have multiple routes, I can do equal cost multipathing. Now there are some ways to change the load balancing mechanism for how the traffic is actually distributed. So if we look at the show Fabricpath load balance, says that the hashing is symmetrical. You could change this around to get maybe a better utilization of the links. But in general, you normally wouldn't have to do this because it's just normal layer 3 logical load balancing that is now being applied down onto the layer 2 topology. Okay, there's a couple questions we have here. Not clear how Fabricpath leaf learns another leaf end node. If it's encapsulated in its own MACs, how does it populate the forwarding database with inner MAC addresses on the leaf nodes? Okay, so there's basically two separate processes that are happening behind the scenes. The first thing that happens is that we start Fabricpath on the links, which means we're initiating ISIS. Okay, ISIS is using its own layer 2 transport, so it's basically sending layer 2 multicasts where CLNS is directly encapsulated on Ethernet. Okay, the CLNS packets are sent back and forth to figure out who are the routers running ISIS, what are their network entity titles, what are the levels, what is the authentication. That's the normal ISIS exchange. Okay, once we go through the adjacency, then we go through the link state database exchange. So I tell you my routes, you tell me your routes. But in this case, the routes are the Fabricpath nodes and then the Fabricpath links that are interconnecting them. So it's the same logic as OSPF or regular ISIS, but now it's being applied to layer 2 routing. Okay, so now we know what does the network look like, who are all the switches, and how do I reach them. Now I didn't yet tell you who are the actual MAC addresses. So the way that this works is if we look at the more specifics of the data plane, when the packet is coming in to Fabricpath. So let's say that we have, and let's simplify this diagram a little bit. Let's look at this within the scope of just a couple of the routers. Let's say that we have router 3 on the left, and we have router 2 on the right. So we're trying to get connectivity between them. It's going in this direction. So the Fabricpath devices already know what the tree looks like, what the SPT, the shortest path tree, looks like based on ISIS doing its calculation. But they don't yet know any of the end hosts. So how do we know about the MAC addresses? It's going to be the same logic as regular MAC address flooding. So router 2 sends a packet into the network. Let's say it sends an ICMP ping. The destination at layer 3 is unicast. Once the switch receives this, it doesn't yet know where the destination MAC address is. So it's both a layer 3 unicast and a layer 2 unicast. So this is assuming like router 2 already knows the MAC address of router 3. So from this switch's point of view, this is an unknown frame. It's an unknown unicast. So I need to flood this. Once it gets into the Fabricpath core, likewise, it is going to be flooded. But when it is in the core, it is subject to the conversational MAC learning. So I'm not actually going to install the source MAC address until I learn the destination, which is going to happen when we elicit a response back from them. But the key is going to be the switches in the middle. They also need to know what were basically the leaf switches or the entry points into the Fabricpath network that I need to switch the traffic back to them. And this is essentially what is encoded inside of the data plane. Now, I'm not able to do it live right now, but let's take a look at the physical diagram right now. And over here on one portion of the network, what I have is an end server that is running Wireshark here. And this Wireshark device, it has a regular Ethernet link here. But the problem is the Fabricpath information is not Ethernet. So if you actually configure this, and I'm talking about trying to capture the frames here. If we're trying to capture the frames for Fabricpath, the problem is that the F1 card is not going to redirect a Fabricpath frame to a non-Fabricpath interface. So basically from Fabricpath, you're going to the classical Ethernet domain. You're not allowed to maintain the header. You have to decapsulate it. You're basically the leaf node in that case. So you end up in this strange situation that you're not actually able to capture the data plane simply because Fabricpath is not Ethernet. So one of the ways that I solved this here was to put an actual layer 1 tap in the network. So there's an additional layer 1 device here, and this is configured now as 1 gig E that's going between two of the 7Ks that is making a layer 1 copy of the frames and then redirecting it to the packet analyzer, to the Wireshark. So I'm not going to look at we're not going to show the actual capture of the frames, but what I want to show is the result of this. What do the actual data plane frames look like? And this is going to be an ICMP echo and reply over Fabricpath. And I'm not sure if I have, let's see, I think I also have the ISIS control plane, which I do. Okay, this one here is regular Fabricpath. Or excuse me, this is not Fabricpath. This is ISIS. Okay, ISIS doesn't get encapsulated in Fabricpath because ISIS runs natively over layer 2. This is the reason why you want to use that for the control plane. So if we look at here inside of the ISIS packets, let's look for an LSP itself, like an actual advertisement. We can see here that there's Ethernet here on the outside, and inside of Ethernet, this is the ISO protocol stack. This is CLNS. So we have ISIS here directly encapsulated inside Ethernet. It's using its own transport. Then inside the LSP DU, the link state protocol data unit, this is the actual routing update. Okay, in the routing update, you're going to have these extended type length values that are actually used to advertise what are the switch IDs. Now, when I was going through this and looking at the details of the LSPs, you'll see that you actually get these unknown packets because Wireshark doesn't know what the frame format is for Fabricpath. Because it's not an open standard protocol, it's a Cisco proprietary implementation. They're just using ISIS with its extensibility in order to advertise these link state updates. So this is basically the routing advertisement, but Wireshark doesn't know how to decode it because it's not a normal standard ISIS update. Okay, then if we look at the actual data plane, this is like a ping, an echo and reply between the two end hosts. And if we look inside the data, basically Wireshark doesn't know what to do with this because it's the full IP packet header. So it's 1,500 bytes plus the additional Fabricpath header on top of it. It sees some of this is Ethernet, but the Ether type is 8903. This is the DCE, Data Center Ethernet, or basically this is the Fabricpath header. But what you would see here in the source and destination, it says the destination address is 020033 coming from 020034. And these are talking about the 5Ks. If I were to open up my calculator here, and in this example I was having the same type of setup we do now, where the switch IDs of the 5Ks were 51 for 5K1 and 52 for 5K2. If we plug this in hex, 33 in decimal is 51. And 34 in hex, decimal is 52. So basically what this is showing us here is that the data plane frame is moving between 5K1 and 5K2. So in the core of Fabricpath, when we receive the packet inbound, we don't do a lookup on the final destination. The only thing that we're actually doing is a lookup on the switch ID and then following the ISIS shortest path tree in order to actually reach that destination. So we do still need to learn the MAC addresses in the core to be able to switch the frames properly, but we're basically doing, again, an Ethernet over Fabricpath tunnel. So regular flooding rules apply, but as opposed to using the conversational learning, as opposed to using the normal traditional learning, we're using conversational learning. Then in the data plane, we're encoding the switch IDs in the Fabricpath header. That's basically similar to logic like how MPLS VPNs work, where we're adding an additional tag on top to say, this is my ingress of the network, this is my egress of the network. You guys in the middle, as long as you can get me to the egress is going to know where the actual destination is. And that's, again, what we saw here when we look at the MAC address table. In the core, when we show MAC address table, it says to get to 0000002, go to switch 52. Or to get to 003, go to switch 51. So based on this, I then can consult the shortest path tree, which is the show Fabricpath route. It says to get to 51, I'm going to go out either this link or this link. They're both an equal cost of 40, so now I can do load balancing between the two of them. And if we look at the show interface E23, and let's look at the include the input rate or output rate. And this is E23 to 4. Notice the output rates. They're equal. So we're essentially doing a one-to-one equal cost multipath or ECMP load balancing on the flows. But again, the flow in the middle here is categorized based on the switch ID. It's not categorized based on the final destination. And this is the way that they're simplifying the control plane on the back end, is that we don't actually route for all the final destinations. We only route for the nodes of the Fabricpath network. So then it makes the scalability much easier. If I want to add additional interconnects, which we could do here if we were to look back at our diagram, and let's say now that I want to add additional interconnects between these two 7Ks. So we could go to the command line here. Let's say on 7K1, I go to interfaces E21 to 2, say switch port mode is Fabricpath, no shutdown. So again, this is not a trunk link, it's not an access port, it's not a switch port, it's a Fabricpath link. Interface E29 to 10, no shutdown, switch port mode. Switch port mode is Fabricpath. We should see a log message now that we established new ISIS adjacency. So now I have a point-to-point adjacency with the level 1 neighbor in 7K1-1. If we now show Fabricpath route, I now know that switch 51 is reachable via E29 to 10, and the links that I just added here were E29 to 10. So I now have a shorter path through the network to route directly between 7K11 and 7K12, as opposed to routing traffic towards the top. So it basically means now all of our traffic flows here between these end servers, they're going to be going in this direction. Because the shortest path tree is closer in this direction between this node and this node to go via this way versus going up here. And we can modify this. The only thing we would need to do is just go and change the cost of the links from the perspective of IS to IS. So you normally wouldn't need to do that. You would just have lots of links that you interconnect the devices, then let it use the shortest path tree in order to try to load balance. And that's typically why in most cases when you look at a physical Fabricpath design, it would look something like this, because we're trying to get as many equal cost paths as possible. So if I were to go to the network and basically turn Fabricpath on everywhere, then I had server 1 trying to get to server 3. My packet can go this way, it can go this way, it can go this way, it can go this way, and then the same on the reverse. So the idea is that none of these links are going to be individually overloaded, because we're doing essentially 8-way equal cost multipath with layer 2 routing. Now, I don't believe there's a practical limit to the amount of links that you can do. It's ultimately going to be based on the hardware, how many physical links that you do have. But adding additional links doesn't necessarily scale the control plane linearly, because it doesn't mean that there are more nodes from ISIS's point of view. And we already know that ISIS is hugely scalable, because service providers have been using ISIS for 15, 20 plus years already to do their layer 3 core routing in large, highly meshed layer 3 topologies. And that's essentially what we're doing here, but we're doing it with a highly meshed layer 2 topology.